So you're gearing up for exams like the ISO, IIT JAM, or maybe CSIR Net. You already know you're not just studying Earth science. You're trying to solve a puzzle the size of a planet. Well, think of this as the cheat code, because today we're going to show you how every single one of those pieces fits together. Let's dig in. You know, these exams can be pretty tricky. They love to throw you a question that on the surface looks like it's about one thing, like atmospheric science. But it's actually a test of a much bigger principle that connects multiple fields. See, they're not just asking what you know. They're asking if you can connect the dots and see the bigger picture. And that's exactly what we're going to do today. We're going to show you that your textbook isn't just a collection of separate chapters. It's all one huge, interconnected story. By the end of this, you'll be building those conceptual bridges and be ready to tackle any question they throw at you. All right, first up, we are going deep. I mean, really deep. We're talking about the colossal engine at the heart of our planet, the powerhouse that shapes everything we see on the surface. Okay, so it all kicks off with the basic structure of the Earth. You've got the crust we live on, the massive mantle underneath, and that super dense core. The best way to think about it is like a giant layered planet cake, right? And the unique recipe of each layer is what drives all the action up here. Okay, so let's talk about a key concept, isosity. The basic idea is that the crust is kind of floating on the mantle. Now that's a great model to start with, but here's a pro tip for your exams. It's not the whole story. Take the Alps, for instance. They aren't just floating there. They're being actively pushed up by these incredible tectonic forces. And that little detail, that could be the difference between a right and a wrong answer. And this is where you have to really wrap your head around geologic time. I mean, a few centimeters a year, that sounds like nothing, right? But you multiply that over millions and millions of years and boom, you're building oceans, you're moving entire continents. It's this super slow motion process that ends up causing earthquakes, building volcanoes, and even changing our entire climate. All right, so we've looked at the planet's engine. Now let's get into the stuff it's made of, the raw materials. We're going to see how the super theoretical chemistry of rocks connects to the real-world challenge of, actually finding and using them.
Okay, eutectic point. I know, it sounds super complicated, but stick with me. It's actually pretty straightforward. Imagine you're heating up a rock made of different minerals. The whole thing doesn't just turn to goo at once. Nope. There's this one specific sweet spot, a perfect temperature and composition, where it starts to melt. That's the eutectic point, and it's the key reason why we see so much basaltic magma on Earth.
All right, enough theory, let's get practical. If you're an engineer trying to build a tunnel, you're not sitting there thinking about eutectic points. You're thinking, is this rock going to fall on my head? And that's exactly where something like the Rock Mass Rating, or RMR, comes in. It's a real-world scoring system that bridges that gap between lab theory and what's happening out in the field. And this is where all that theory pays off. Literally. Because if you know your rock types, you have a pretty good idea of where to look for valuable stuff like copper or zinc. It's basically like having a treasure map that's written in the language of geology. But that leads to the big question, right? How in the world you find these resources when they're buried deep underground? You can't just start digging everywhere. You need a way to, see through solid rock. And the answer is geophysics. We use all these clever techniques, like resistivity surveys, to basically build a picture of what's going on down there. So a question like this on an exam, it's not just some abstract math problem. It's a simulation of how we use physics in the real world to find buried treasure. Okay, so far we've been looking at huge planetary scale stuff. Now we're going to do the opposite. We're going to zoom in. I mean way in. We're about to see how the absolute tiniest of creatures can tell us the most epic stories about our planet's history. Just look at these. I mean, seriously, they look like something out of a science fiction movie, don't they? But these are the fossilized skeletons of ancient plankton. And they're more than just beautiful. They're tiny, perfect time capsules that tell us exactly what Earth's climate was like millions of years ago. But here's the catch. As these little time capsules sink down into the ocean, they face a major threat: deep ocean water. See, as they get deeper, the water becomes more corrosive, and they literally start to dissolve. It's this frantic race against time, and frankly, a lot of them just don't make it to the seafloor. And this brings us to the CCD, the Carbonate Compensation Depth. It's a really crucial clue for understanding Earth's past. Basically, it's the depth where these shells dissolve faster than they can accumulate. And what's really cool is that this depth has changed over geologic time, telling us a ton about how the oceans and the climate have shifted. It's like finding a fossilized chemical fingerprint of the ancient deep sea. All right, we've been deep inside the planet. We've traveled way back in time. Now, let's come back to the surface and see how the landscapes we know and love are being sculpted as we speak. You know, in geology, the details are everything. Take something that sounds simple, like a shoreline moving seaward. Well, it can happen for two totally different reasons, and each one leaves a completely different signature in the rock record. It's kind of like the difference between an orderly retreat versus a chaotic, forced evacuation. The outcome looks similar, but the story behind it is totally different. And here's a classic example you'll see on an exam. They'll show you a picture of a landform and ask you, what made this? In this case, these specific types of dunes, barchans and transverse dunes, are a dead giveaway. They only form when the wind is consistently blowing from one direction. The land itself is telling you a story. You just have to know the language. Okay, so here's the whole point, the bottom line. None of these subjects, geodynamics, petrology, paleontology, exist in a vacuum. They are all pieces of the exact same puzzle. So let's look at one final question that's really going to put your connecting the dots skills to the test. All right, this is it, the final boss battle. You've got statement A, which links the last ice age to sea level. Then you have statement B, which links it to the chemistry of tiny little plankton fossils. I mean, on the surface, they seem completely unrelated, right? Well, let's find out. Okay, watch this. This is where everything connects. First, glaciology. The last glacial maximum means huge, massive ice sheets. Where does that ice come from? Ocean water. So that means the sea level actually drops a lot, which makes statement A incorrect. Now for paleoceanography. When water evaporates from the ocean, the lighter oxygen isotope, that's oxygen-16, gets trapped in all that ice. That leaves the ocean richer in the heavier oxygen-18. And finally, paleontology. The little foraminifera living in that ocean build their shells out of that heavy oxygen water, so their fossils will have a higher ratio of it, which means statement B is correct. Boom. You just used 4 different fields of earth science to solve one problem. And that, right there, is the secret. It's the key to acing these exams, and honestly, to really understanding our planet. It is not about just memorizing a million different facts. It's about seeing how they all connect. It's realizing that it's all one giant, amazing, interconnected system. You know, we've really only just scratched the surface. We've seen how the deep Earth's engine connects to the resources we use, and how the smallest fossils can tell us about the biggest climate shifts. The real question now is, what new connections are you going to discover in your own studies? This planet is just full of secrets, and now you have the tools to start uncovering them.